Uh, Thank you, Sri. Hi, everyone. I'm Yegan Zhang, and I'm leading geometric vision at Autopilot. So, yeah, let's talk about auto labeling. So we have several kinds of auto labeling frameworks to support various types of networks. But today, I'd like to focus on the awesome lanes net here. So to successfully train and generalize this network to everywhere, we think we went tens of millions of trips from probably 1 million intersection or even more. So then how to do that? So it is certainly achievable to source sufficient amount of trips because we already have, as Tim explained earlier, we already have like 500,000 trips per day cache rate. However, converting all those data into a training form is a very challenging technical problem. To solve this challenge, we've tried various ways of manual and auto labeling. So from the first column to the second, from the second to the third, each advance provided us nearly 100x improvement in throughput. But still, we want an even better auto labeling machine that can provide us good quality, diversity, and scalability. To meet all these requirements, despite the huge amount of engineering effort required here, we've developed a new auto labeling machine powered by multi-trip reconstruction. So this can replace 5 million hours of manual labeling with just 12 hours on cluster for labeling 10,000 trips. So how we solved? There are 3 big steps. The first step is high-precision trajectory and structure recovery by multi-camera visual inertial odometry. So here, all the features, including ground surface, are inferred from videos by neural networks, then tracked and reconstructed in the vector space. So the typical drift rate of this trajectory in car is like 1.3 centimeter per meter and 0.45 milliradian per meter, which is pretty decent considering its compact compute requirement. Then the recovered surface and road details are also used as a strong guidance for the later manual verification step. This is also enabled in every FSD vehicle, so we get pre-processed trajectories and structures along with the trip data. The second step is multi-trip reconstruction, which is the big and core piece of this machine. So the video shows how the previously shown trip is reconstructed and aligned with other trips, basically other trips from different vehicles, not the same vehicle. So this is done by multiple internal steps like course alignment, pairwise matching, joint optimization, then further surface refinement. In the end, the human analyst comes in and finalizes the label. So each heavy steps are already fully parallelized on the cluster. So the entire process usually takes just a couple of hours. The last step is actually auto-labeling the new trips. So here, we use the same multi-trip alignment engine, but only between pre-built reconstruction and each new trip. So it's much, much simpler than fully reconstructing all the clips altogether. That's why it only takes 30 minutes per trip to auto-label instead of several hours of manual labeling. And this is also the key of scalability of this machine. This machine easily scales as long as we have available compute and trip data. So about 50 trips were newly auto-labeled from this scene, and some of them are shown here. So 50 trips from different vehicles. So this is how we capture and transform the space-time slices of the world into the network supervision.
Yeah, one thing I'd like to note is that Yegan just talked about how we auto-label our lanes. But we have auto-labelers for almost every task that we do, including our planner. And many of these are fully automatic. There's no humans involved. For example, for objects, all of the kinematics, their shapes, their features, everything just comes from auto-labeling. And the same is true for occupancy, too. And we have really just built a machine around this.
Yeah, so if you can go back one slide. One more. It says parallelized on cluster. So that sounds pretty straightforward, but it really wasn't. Maybe it's fun to share how something like this comes about. So a while ago, we didn't have any auto-labeling at all. And then someone makes a script, it starts to work, it starts working better until we reach a volume that's pretty high and we clearly need a solution. And so there were 2 other engineers in our team who were like, hey, that's an interesting thing. What we needed to do was build a whole graph of essentially Python functions that would need to run one after the other. First you pull the clip, then you do some cleaning, then you do some network inference, then another network inference, until you finally get this. So you need to do this at a large scale. So I tell them, we probably need to shoot for 100,000 clips per day, or like 100,000 items. That seems good. And so the engineer said, well, we can do a bit of Postgres and a bit of elbow grease. We can do it. Meanwhile, we are a bit later, and we're doing 20 million of these functions every single day. Again, we pull in around 500,000 clips, and on those, we run a ton of functions, each of these, in a streaming fashion. And so that's kind of the back-end infra that's also needed to not just run training, but also auto-labeling.
Yeah, it really is like a factory that produces labels, and it's like production lines, yield, quality, inventory, like all of the same concepts apply to this label factory that applies for the factory for our cars.
That's right.
Okay, thanks, Tim and Ashok. So concluding this section, I'd like to share a few more challenging and interesting examples for network, for sure, and even for humans, probably. So from the top, there's like examples for like lack of lights case, or foggy night, or roundabout and heavy occlusions by parked cars, and even rainy night with the raindrops on camera lenses. These are challenging, but once their original scenes are fully reconstructed by other clips, all of them can be auto-labeled so that our cars can drive even better through these challenging scenarios. So now, let me pass the mic to David to learn more about how Sim is creating the new world on top of these labels. Thank you.